button here. Okay, and number 28, we'll put here 1252 after we did a question, interesting enough, on really that was physics 123 question. So I didn't record that one for that reason. Okay, so let's go ahead and I'll share my screen. Oh, I already am sharing my screen. That's right. And then let me switch to the questions. All right, so 28, let me read it together here. 28 says a 10-volt battery, a 5-ohm resistor, and a 10 Henry. As I was mentioning in the other session, you start getting up into the Henrys and out of the millihenries. These are big inductors and often regarded as chokes. So I think I might call this a 10 Henry choke. So big and chokes the circuit. Is connected in series. So let me just kind of draw kind of that basic circuit that we were doing. One of these circuits, I think that like number 11. So here's the 10-volt battery. And let me put a switch in here, switch. And since they're in series, it won't matter which one I put first, the inductor or the resistor. And so I see that they listed the resistor first, so I'll put that. So 5 ohms for that resistor and 10 Henrys for the inductor. Okay. It says after the current in the circuit has reached its maximum value. Okay, so what they're saying here is, I guess, we close the switch and wait a long time. And without specifying how long, we're really trying to say that after a while, and this is the key to that phrase, after a long time, and I'll just repeat it. We did, again, same thing in number 11. We say that the voltage in the inductor is minus L di dt. But if you wait a long period of time, the current in the inductor doesn't change anymore. It settles down. In fact, we learned this little equation that a simple LR circuit here would have nothing until you close the switch, and then it would exponentially climb up to this value of the EMF divided by the resistance. So we can kind of see that, or just derive it by saying, look, after a long period of time, the voltage from the inductor is 0. And so I'm going to use the same phrase I used in number 11. If you ever come across a problem that says, hey, it's been there for a long time, it is really a nice way of saying that the current is no longer changing with time. Oh, by the way, let me pause right there. Whoa, yeah, because I got to put a qualifier in there. That would be for a DC circuit. Because if you had a circuit where the voltage kept changing, then you would never reach a point where the current stopped changing. And you would never get this to be 0. And so we're going to have that discussion in chapter 33, the next one. Kind of the main difference between this chapter and next chapter is next chapter, we make our circuits hooked up to power supplies that constantly change their voltage. And hence, we never get a situation like this. We never get a place where the current stops changing, and it never settles out at some maximum or final current. But, okay, that's getting ahead of myself. So, but for this one, we can say that after a long period of time, things settle out, and the current doesn't change. Because the only reason the current is changing is because we close the switch and things are building up to some constant value. They're not changing because the power supply changes. And like I said, if that was the case, then we might get to a point where we never have the current settling out, and that's coming. But for this chapter and for this week, and I'll just say there would be a time where maybe on this time scale here would be someplace where the current no longer changes with time. And so a result of that is the voltage is zero. And a result of that, I'll put a different maybe color here, maybe red, but you can think of this circuit as if the inductor is not even there. The inductor is just a wire. And so it's a what we call a short circuit. And so a phrase to keep in mind, if you have and I should say the qualifier, if you have a DC circuit, all right, if you have a DC circuit and you leave the switch closed for a long time, you can treat the inductors as just a wire. It's exactly the same idea we said with capacitors, although capacitors, we said, after a long time, they fill up and block the current. And so the current would be zero in that branch where the capacitor is. Whether the capacitor blocks the whole circuit or just a sub branch of it, it blocks it. And so after a long time, we said capacitors are treated as an open circuit. Inductors are exactly the reverse. Okay. So keeping that in mind, however you want to get there, either by going to the book or doing kind of a loop where you call the voltage here at zero, you would just say 10 volts minus 5R, that's Ohm's law, and then minus zero for the inductor equals zero. If I do this whole loop after a long period of time, just simply means that the current would be 10 over 5, which is 2 amps. So that's kind of the first thought process that goes on when I see number 28 here, when they use that phrase. After the current in the circuit has reached its maximum value, which is also a way of saying it's reached its steady state or it's reached its maximum long-term value. All right, so I needed to know what that was. And so that's why I kind of went through this little discussion knowing, okay, so if this switch has been closed for a long time, 2 amps are racing through it. So now we can say then calculate the power being supplied by the battery. All right. Well, power is the current times the voltage. That goes way back to our circuits. And so I think that's chapter 27. But of course, in order to do that, we need to know the current. So that's why this first part was important about the inductor. So this would be a current of 2 amps, and the battery has a voltage of 10 volts. And so that comes out to be 20 watts. So I would say the power being delivered, so the power being supplied by the battery is 10 watts. 20 watts. It'd be 20 joules every second. Okay. So B here would say the power being delivered to the resistor. Now, this would kind of be the same thing, current times voltage. Now, again, since they're just a simple series circuits, and I shouldn't probably use simple. I mean, series are the simplest of circuits, as we saw, but these do get pretty hard once you put in an inductor. So we, by the way, are only going to go that far. We're going to just, learn about inductors, and because inductors are really the application of Faraday's law. So our goal here this semester is to learn about Faraday's law, and one of the applications of that is in a circuit. And then there's many complicated circuits we could have. So keep in mind that we're just going to give you the simple ones because you guys are going to be in circuits, maybe, most likely. I'm going to encourage you. Well, maybe you're already there, but you're going to do much harder circuits in a circuits class than this one. So this is a good first step to understanding our circuits. And again, our goal really isn't about being knowledgeable in circuits as much as it is being knowledgeable in Faraday's law and how Faraday's law can be used with an inductor and can be used in a circuit. That's probably the bigger picture. But that in mind, then again, looking at the power here, being the resistor, we can again do the same thing, I times V. We could do I squared R, and I'm probably more tempted to do that one for the resistor because since it's in series, I know this is 2 amps, so I can square it. And I know the resistance is 5 ohms. And so running through the math, 2 squared is a 4 times a 5 is a 20 watt. But of course, not a surprise that this would work too. I know that there is 2 amps, and the voltage, as we just said back here with the loop, you go all the way around the loop, you have to get to 0. So if you go up 10 because of the battery, and we're talking about during the steady state, so there's no voltage here, you would have plus 10 minus something, minus 0 gets you back where you started. So this has to be a 10. And so you could go 10 volts, which again leads to your 20 watts. So whichever way you want to tackle this one. And notice it's probably not a surprise that the energy being delivered by the battery is being consumed by the resistor. Again, that's because really at this point, we're at steady state, nothing interesting is happening with this inductor. This inductor has built up to a certain current. Therefore, it has built up to a certain strength in its magnetic field, which means it's storing a certain amount of energy, but it's not increasing its current. So it's not absorbing any energy. It's also, for that matter, not delivering any energy. There is no increase or decrease in the field because the current isn't changing. So there is no increase or decrease in the energy. And so the energy changing with time, the power would be 0 on this. So it's not a surprise that the power delivered by that has to be all on the resistor, because there's nothing here. I mean, technically, the power delivered by the battery would have to be equal to power being consumed by each of these. And if that one's 0, then that one's got to be the total, and that's why we get a 20 in step B. All right, so in step C, we can go the power being delivered to the inductor. Well, I guess I already said it, but I'll do it again. Power is the current times the voltage. And again, the current in the inductor at this point is 2 amps, but again, at steady state, the current isn't changing. I'm going to go back and read it. Did I read it right? Because it's kind of a boring problem so far. There's nothing changing. A 10-volt battery with 5-ohm resistor and a 10 Henry inductor are connected in series after the current in the circuit has reached its maximum. So afterwards, calculate. Well, this is what they want. Maybe they, want us to realize that. Anyways, the voltage is 0 because this is the voltage. This is the EMF. It's minus L di dt, and di dt is 0. So it's a 0 watts. And of course, not a surprise that the resistor and the inductor add up to what's being delivered by the battery. Just kind of boring at this point because we've waited so long that nothing new and different and exciting is happening in the inductor. But maybe that's what they want you to realize. It's not changing. However, look at D. D does say what is the energy stored in the inductor. Now, they say in the magnetic field in the inductor, so I should say that, but hopefully that's where you realize where the energy is. And I like to draw my magnetic fields in green. So maybe I'm going to give this inductor a field in green. And so there's a lot of energy stored there. So during the transition of us building up to 2 amps, there was energy being delivered to the inductor. But eventually, when it builds up to its maximum value, then it doesn't change anymore. So that's why our power is 0. So remember, the power is the rate of change of energy. So there is no rate of change, but there is a constant energy value because there is a constant magnetic field, which comes from the constant current. And this is where the 1/2 Li squared comes into play for how much magnetic energy, or maybe I should just say energy, but it is energy stored in the magnetic field, is here. And that's just looking at it in terms of current and inductance. That's by the way, similar to what we did, let's see, I guess it was number 24, right before the break. We had a solenoid and we looked at the energy, but we never looked at the inductance or the current of it. So we didn't look at it in terms of a circuit. We looked at it in number 24 more in just as the basic physics, that there is an energy density and that there is then a field. And we just calculated the energy based upon the energy density and then used that energy density and volume to get the energy. We never went back to the inductance of the current, but we could have. We could have looked at it like a circuit. But I think for this problem, we should be looking at it as a circuit. In fact, my only maybe complaint about this equation is that it hides the fact that the energy is in the magnetic field. There is nothing in this equation that says be the magnetic field. However, magnetic fields do come from the current. So that's the real positive about this equation. This equation is saying there's energy stored because there's current. And I'd say, yeah, because there's current, there's a magnetic field, and because there's a magnetic field, there's current. So this kind of goes from the basic current to the second step of there's energy, and it kind of skips over the magnetic field. So very useful equation, and it's perfect for this particular problem because we can put in the 1/2 and we can put in the 10 henries, and we can now put in the current of 2 amps and square it. So the 2 squared would be a 4. 4 times a 10 is 40. Half of that is 20. So there'd be 20. Now it's going to come out to be joules, but maybe this would be a good time, like I did on one of the other problems, to say maybe we should look a little carefully at the units just to make sure things are working out right. And a Henry comes from the definition of the inductance. Quick call out here. An inductor gets its EMF from the change in the flux. And the change in the flux comes, in a circuit anyway, from itself. So as we work through how much the flux, we'll see that the flux actually comes from current. And the reason the flux changes is because the current changes. So everything else in the flux, like the size of the solenoid, if it's a solenoid, and that's part of it. What shape is it? Is it a solenoid? Is it a toroid? You know, what shape do we have? Is it a coaxial cable? But all of those factors that have to do with the flux can be pulled out into the number of turns and buried into this L for the inductance here. So this is our fundamental physics. And then applied to itself in a circuit, this would be a good way of writing it in a circuit. But then what that means is you can then write inductance as the magnitude of the EMF divided by the rate at which the current is changing. So if you give honor to, I think it's Joseph Henry. No? I might be confusing that with something else. But Henry, last name, you give honor named after him, like we do with joule and ampere, or ampere, amps. We give a unit after this. And so I like to just jump back here and say, well, what is a Henry? A Henry, 1 Henry means you would get 1 volt of back EMF when the current is changing at 1 amp per second. So using that in this equation, I would call this Henry a volt over an amp per second. And then up here, I would have amp squared, canceling off one of the amps and leaving me with a volt times an amp in the top. And then the second flips up and gets a second. Remembering that a volt is a joule per coulomb. An amp is a coulomb per second. And so when we multiply by seconds, you can see that not only do seconds cancel, but so do coulombs, and you're left with joules. So the energy that is that has already been stored. So it took a while. We don't know how long. We weren't asked to calculate it, but it will take a little while, and this is a big inductor. My guess it would at least be a couple of seconds, but it kind of depends on the value of the inductor as well as the resistor. Usually we say it takes 3 time constants. So if I take L over R, L is 10 and R is 5. So that's, so 2 seconds is 1 time constant. So 3 of them is 6 seconds. So I would say roughly after 6 seconds. So it's going to take about 6 seconds for this to build up. 3 time constants, I think, gives us 98% the way there. And I think 5 constants gives us 99.5%. I should check those numbers. What is E to the negative 3? Just out of curiosity. So E to the negative 3. Okay, so it's only 95%. So 3 time constants is okay, but it's only getting us to 95%. So after 6 seconds, we're about 95% to our stored energy. So -5, if we want to be a little more closely connected to getting there. Oh yeah, 90, it gets us to 99.3%. Okay, I should memorize those numbers. All right, so a better statement is not 3 time constants. That's only, that's still 5% off. But 5 time constants gives us really close, 99.3% of the way there. All right, so 2 times 5 is 10 seconds. So maybe I should say after 10 seconds, we essentially have now completely energized the inductor. We now have 20 joules of energy. Good to go. We can say it's completely full and the current is now stable after 10 seconds. Nice. And like I always like to do, let's just check 20, 0, 20. Nice. All right. So that one seems straightforward enough. So, all right. So I'll move on to your next question on your list and make a note of it in the time. Let me find your list. Here it is, number 37. So 37, and I'll start this at 114. 37. And just out of curiosity, before I begin, if there was anything added to the chat. You guys chatting between your major? Good. MATLAB course, good one. Yeah, okay. MATLAB's a good course. Oh, and you're a CS major, huh? Oh, good. Well, that's probably why you're doing really, really well in computer science, as James said. But you're doing great in here, actually. My computer science students, not always, but a lot of times, since engineering's not their strong suit, they kind of I don't take it maybe as seriously as they could, and I understand that. I'm not complaining. I know their focus is on computer science. So, congrats to you for really taking this as serious as any engineering student, knowing that your career and highly depends on it. Whereas you're doing coding, I don't think your career depends too much on electromagnetics, but I think it dramatically helps understanding the world around you, especially some of these games. I like when they make the games more realistic. And I'm old enough to go back way when the games were they're so funny. They had this kind of the first like Atari stuff when somebody would die. I mean, it was just a little pixelated man. It didn't even really look like a human. It just pixelated, and it died the same way that just the pixelated figure just kind of crumbled, and it always fell that way. And then it didn't matter which side you dropped the hand grenade on, it would always crumble that same way. So it just looked weird when you drop the hand grenade on this side, it goes off, and the little person crumbles in that the same direction as the blast. Like, okay, but that really wasn't an issue of not knowing physics. it was an issue of the processors couldn't handle that much graphics and that much processing power. All right, but I digress here. All right, so let me come back to 37. Oh, and I noticed 37 would be on that second page that's missing. So I printed up that second page because I sent it to you, but sadly, it's rotated 90 degrees, and it's driving me crazy looking at it 90 degrees. So I printed it up here. So I thought, well, I'll just print it up, and if anybody asks from the second page, I'll just put the piece of paper in here. So here it is. It says a 1 microfarad capacitor is charged by a 40-volt power supply. The fully charged capacitor is then just discharged through a 10 millihenry inductor. Find the maximum current and the current in the resulting oscillation. So we don't have to worry about knowing that it oscillates. They're essentially telling us that, but I'll hook up a circuit that you might actually build for something like this. So maybe you'll take your power supply. So here is the 40 volts. And maybe then I will hook up the capacitor. And here's where I'm going to put what we call a single pole double throw switch. And I'll just put the switch kind of in the neutral position. And maybe so we don't try to charge up our capacitor too quickly and do some damage, maybe I'll put a resistor here. But the reason we call this a single pole double throw switch, as trying to draw in this diagram, is we can move the metal piece over to here and make this connection. And that would charge up our capacitor. And in this case, it would keep charging it, keep charging it, keep charging it. And after a long period of time, we would get 40 volts on the capacitor. And so I think that fits this first part. And maybe I should put C equals 1 microfarad. So we put a 1 microfarad capacitor and we charge it by a 40-volt power supply. Now, they don't really tell us how they charge it, but the most you could charge it to is 40 volts, and we could do a bunch of other resistors and get less. So I think they want us to do something like this. I think they want us to charge it to 40 volts. But then we can disconnect it from the battery. So this is why we move the pole of the switch to the other side and make a connection there. And now you can see why it's a single pole double throw switch, whereas a lot of the switches I've been talking about look like this, kind of like a light switch. You just have a single pole and a single throw. It just makes a connection or doesn't. And so the switch is either on or the switch is off. It's the easiest type of switch. It's a single pole, single throw. But this is a single pole double throw. And so we throw it this way. And so I think they're saying here, now hook this to an inductor. So it says here, a fully charged capacitor is then discharged through an inductor. So once we disconnect it, we have it charged, and we're going to let it then flow out or discharge through this inductor. Okay. And that means we have a circuit called an LC circuit. See, our LC circuit then oscillates. It starts off with all of its energy on the capacitor. You might say it starts with all of its energy in the form of an electric field. And as it discharges it, it takes that charge and makes it flow, so it builds up a current. And so what we end up with, if I can maybe do a green and a burnt orange, is that the energy that is first stored in the electric field between the plates of the capacitor begins now to diminish and go away. Where does it go? Well, it goes to the energy stored in the magnetic field. And eventually, all of the energy in the capacitor. So the electric field goes completely away. That means there's no more charge on the capacitor. And it has built up at that point to its maximum current. And so all the energy is stored in the magnetic field. Now, the reason we say this oscillates is because it doesn't stop there. Then what will happen is the energy in this magnetic field will keep the current flowing and basically start to charge up the capacitor in the reverse direction, transferring all of its energy from magnetic energy back into electrical energy until the capacitor gets charged again. You might even call it a reverse charge, because now the capacitor has a bunch of pluses on the bottom of it and a bunch of negatives on the top. But essentially, eventually the current stops and you have all of your energy in the electric field and nothing in the magnetic field. And then it does that back and forth, just sloshes back and forth. And so if you were plotting the charge as a function of time on this capacitor, you would start with the top plate very positive, and then after what we call a quarter of a cycle, it would all be gone. You'd have no charge here, and that's the moment when you have the full current. Then it continues to build up a charge in the other direction. So the top plate, this is what I'm plotting, is the charge on the top plate, would now become negative. Then it would slosh back to zero and then slosh back to positive, and the pattern would continue. And so this is your oscillations. And this problem isn't really asking for us to prove that it oscillates. It's not asking us to prove what the rate of oscillation. I think that's coming up with your other questions. There's problems like that. This one is asking for, and I think, the maximum current. Find the maximum current. And there are different ways of doing this. Here's what I think is the easiest way, is to recognize that all the energy in the electric field is going to eventually become an equal to all the energy in the magnetic field. So that means 1/2 CV maximum squared. From that, we got to go back to the energy stored in our capacitor. So going back to chapter 26, this is the energy in the capacitor. Okay, where does it go? It eventually goes all into a magnetic field in the inductor. And so using that same equation for the energy stored in an inductor that we just kind of talked about in the last problem, I guess was 28, this then would be the maximum current. Now, I want to emphasize that maximum voltage and maximum current do not occur at the same time. So when I'm saying they're equal, yeah, they're equal in the magnitude of their energy, but it's like a pendulum swinging. As the pendulum swings back and forth, we could say that, the potential energy on one side later on is equal to the kinetic energy at the bottom, which later on is equal to the potential energy on the other side. So we're not saying they're equal at the same moment in time, and I just want to emphasize that. But we are saying they are numerically equal. And so when we do this, the thing we don't know is the current, and we know everything else. So if I just start by canceling off a 1/2, I can then put in my numbers. They said the capacitance was a 1 microfarad capacitor. We are going to charge it up to 40 volts before we move the switch over to discharge it in the inductor. The inductor doesn't look like I wrote it on here, so let me come back. What did it say? 10 millihenries. So 10 millihenries. I'll put in my diagram. But over here, then I'll go 10 times 10 to the minus 3, and that would be the maximum current squared. So then I can get out my calculator here and say, all right, let's go 1 times 10 to the negative 6 times 40 squared. then I will divide by 10 times 10 to the negative 3. And that would, I guess, be the square of the current. So taking the square root gives me 0.4 amps. And there's no part A or B or C. And again, before we move on, I'll check 37 and scroll down here. Whoops, too far. Yeah, 0.4 amps. Nice. Nice. Okay. Sure. Another good set of questions. I'll move on to the next one here. All right, so the next on your list was number 40. Okay, so let's do number 40. I'll put in a time of time is 1:27. Maybe I'll put here number 40. And let's read that one. Oh, and that would be on this sheet also. Okay, so number 40 says an LC circuit like the one in figure 10. And I'm going to say like what we just did back here in problem 37. So one capacitor, one inductor. So maybe I'll just draw that first. Okay, so one capacitor and one inductor. And so again, if we initiate it with some energy, which in the last problem, we initiated it with some energy stored on the capacitor, it's going to slosh back and forth at some rate. So keep that in mind. Okay, so we have this C and this L. Maybe I'll write in their values. An LC circuit like the one shown in figure 10 contains an 82 millihenry, 82 millihenries for the inductor, and a 17 microfarad, so 17 microfarad, that initially has a charge. Okay, so I'll call it Q naught, 180 microcoulombs. So unlike the last problem where we knew what the voltage started at, which we could have figured out what the charge started at. In fact, I plotted charge, but I never figured out what the charge was because I didn't need it for the problem. This one, we don't know exactly what the voltage is, although we could figure it out. We're told what the initial charge is. So not too much different so far. The switch is opened for time less than 0. Now, I didn't put a switch in here, but I'm going to take a moment to look at this. I have a feeling this is it, that there's a little switch, and once the capacitor is charged, nothing will happen until you close. But I better confirm that. So let me go to the book here. And, I went to 40, but that's not what they said. They said it was in figure 10. Let me go to figure. Yeah, here it is. So figure 10 down here has a capacitor, an inductor, and a switch. It doesn't matter where you put the switch. You can't discharge the capacitor until the switch is closed. So my drawing has it up at the top and theirs is at the bottom. Other than that, I'm talking about the same thing. So I'm just going to leave my switch up here. Okay. And so then I'm going to close it. And I think that's what they're after. The switch is open for time less than 0 and then thrown closed at time equals to 0. A, find the frequency in hertz of the resulting oscillation. And then the next question begins. I'll just do that, find the frequency. So maybe I shouldn't go through the derivation as much as say that the angular frequency works out to be the square root of L over C. And let me kind of direct you to either the book or the video lecture if you wanted to kind of see that worked out. But again, they just write out Kirchhoff's law and then solve the differential equation. May even kind of remind you, it looks like what we saw in Physics 121 with a block on a spring. Oh, no, my apologies. Half of you have not seen this. The block on a spring is done in Physics 123, chapter 15. So half of you have seen this comparison, but the other half of you have not. So maybe this isn't a good comparison. Your author does it because he's over here in chapter 32 thinking that you did everything in order. And we don't quite do it in order just because we don't have the student population to do that. But I'm not complaining. I think the order we do it is fine. That's why we kind of broke it the way it is. That way you could take either Physics 122 or 123 once you've taken 121. You have to take 121. There's no way to do any more of the book without that, but you can do some of these oscillations. Anyways, he goes through this derivation and gets this omega equals 1 over the square root of LC. Okay, so that's what I have. Oh, 1 over. I wrote that, and I apologize. Meant to do that. It's not the square root of LC. It's 1 over the square root of LC. Okay, so this is the angular frequency. Now, the regular frequency and what we often call the linear frequency, or just the frequency, because this is the number of oscillations. See, angular frequency is like the wheel going around. So we saw angular speed and angular frequency when you're talking about a wheel. Maybe I'll draw a picture because we didn't really get a chance to talk too much about it in 121, mostly because we talk about it a lot more now and also in Physics 123. And your author's kind of assuming I've gone through chapter 15 and you haven't. So I should say something here, but if something is going around this little knob here and it makes one oscillation all the way around, we would in say 1 second, we would say its frequency is 1 cycle per 1 second. And we often write that as 1 hertz. But the reason we call this its angular frequency is because if you're talking about how much angle it rotates, it would go a full circle. So it would go 2 pi radians per second. So this 1 revolution, the angular frequency, would be 2 pi radians per second. And maybe you can begin to see that mathematically, the connection between these two is this factor of 2 pi. In other words, for every 1 revolution of the circle, the radians it goes around is 2 pi. So that's why I'm saying if you take the number of times it goes around in a second, 1, 2, 3, 4, whatever, and multiply it by 2 pi, you're going to get its angular frequency. And sometimes we're a little lazy and not making it clear whether we're talking about an angular frequency or just the regular frequency. But I think the author was particular here. If you look at number 40, it does say find the frequency. So he doesn't say angular frequency, he says the frequency. And he also says in hertz. So that's another indication that we're talking about the F, the regular frequency. So putting these two things together, I would say the regular frequency, just the frequency. I should stop calling it the regular frequency, but I want to point out it's not the angular frequency. Would simply be the omega divided by the 2 pi. And then the omega for an LC circuit is the 1 over the square root of LC. And so that's what I'm going to put into my calculator here in order to do this calculation. So I'll start with this square root of LC. So L is 82 millihenries. C, what was C? 17? I wrote down micro. Is that right? That sounds funny. 17 micro. Yeah, okay. So 17 microfarads. I'll multiply those together. I'll take the square root of that, and then I'll take the reciprocal of that. So that right there is the omega. So now if I divide that by 2 and also divide it by a pi, I get about 135. So 135 hertz would be the frequency. All right. Calling this page 1. That's A. Go to page 2 because I know there's a B here. I didn't read it yet. It was coming up. Okay. At 1 millisecond, find B, the charge on the capacitor, and C, the current in the circuit. Well, let me start with the charge, because the charge oscillates. Right. This was my discussion in the last one that says the capacitor would start with a positive charge or negative, depending on which way you charge the capacitor, but it would be oscillating at some angular frequency. So it would be this, it would be some maximum charge times cosine omega t. Now notice I picked cosine, it's a sinusoidal. And I know the omega is the angular frequency, so that's just the mathematics, and that's the kind of the neat thing about an angular frequency. Some people ask, if I come back here to A, why do we have both an angular frequency and a regular frequency? Well, it's because regular frequency, I think, is how we think. We think about how many cycles per second, but angular frequency is what we need in our math, because when we do a trig function, one cycle has to go 2 pi radians. So we need angular frequency for the mathematics for the trig functions. So it's part of the trig functions. So that's why I'm going to put in here the frequency as this omega. Okay. Now, maybe then I can put in my numbers. They told me what we charged this thing up to. This was 180 microcoulombs. Then I have the cosine, and we didn't actually solve for omega, or at least write it down. It's still in my calculator. If you remember, we did do this omega right here. It was this 847, if I round it, before we divided by 2 pi. So I'm going to use that 847 multiplied by t. So there would be a mathematical description of how the charge changes in the capacitor as it oscillates up and down. Okay. So back to the question. It says at 1 millisecond, find the charge. So I can just plug and chug it. So 180 microcoulombs times the cosine of 847 multiplied by, and I think I read, I need to double check, 1 millisecond. So times 10 to the minus 3. Now, the other thing I might want to be very, very careful for, and you kind of saw it back here in our discussion about what is frequency, regular frequency versus angular frequency. And since we did one revolution is 2 pi, please remember that angular frequency is then written in radians per second. Now, the reason that's important is because if the units is radians per second, and then I multiply by seconds, that's perfect. I don't want to use milliseconds here. I want to use seconds. That would cancel off. And then also notice it would be in units of radians. So looking at my calculator mode, I believe I'm in degrees. I am. So before I go further on this problem, let me switch my calculator into radians. And so I do need to recognize that, otherwise I'll get a wrong number here. So I will then take the cosine of 847 times 10 to the negative 3. And so that's about 66%, about 2/3. So there's going to be about 120. Oh, and I divided, sorry, by 180 instead of multiplying. Let me fix that, and now let me multiply by 1. Yeah, and very close to 120. Would be closer to 119. Okay, so there would be the charge. Now, as for the current, well, the current is just the rate at which charge is changing. So if we have an equation up here for the charge, let's just take its derivative and we'll get the current. This is really very similar to physics 121, where hey, if we had an equation for position and you ask for velocity, take its derivative. And for that matter, if you were asked for its acceleration, take the derivative a second time. We could ask that. I don't know if the author is going to ask, but I would say the first derivative of charge gives me my current. And if I took the derivative again, I would have the derivative of the current, and that would be appropriate if they were asking for, say, the voltage on the inductor, because notice that the voltage on the inductor is how the current changes. So if you have an equation for charge, the first derivative would give you current, and the next derivative would give you the rate at which current is changing, which is the EMF on that inductor. So I'll keep reading, and I kind of hope they give me a part D that says, hey, what is the voltage on the inductor? In the meantime, let's do the current. And they're in series. They're just looped around. So I don't know if you want to call it series or parallel at that point. It's hard to separate a meaning between them. I'll just say this is the current. Whether you want to call it the current in the circuit, the current in the capacitor, the current in the inductor. And I think their question was very explicitly the current in the circuit. So it's all the same. See, and there is no part D. I think this could be a little stronger problem. Part D, what is the voltage in the inductor? Having me do the derivative again, but we just need to do it one time here. All right, so let's come back to this equation, and I will do the 180 microcoulombs for that constant. And now I'm going to take a derivative of a cosine function. Derivative of cosine would be, I got to think here, is it sine or negative sine? Let's see, it's being negative sine. So I'm going to put a negative times sine. And it would be, again, that 847t. And then the chain rule would pull out the angular frequency of 847. We can debate on the plus or minus here because technically this is the charge on the capacitor. So when I take the derivative, this is how the charge is changing on the capacitor. So in a circuit like this, if it's leaving the capacitor, it's going into the inductor. If I really am saying honestly, this would be the current in the capacitor, where the inductor would be the opposite of that. So because of that, I'm going to go ahead and drop that one. But I don't know if that is really relevant, especially in the sense that it depends which way you're talking about. Oh, and they didn't say the inductor anyway, so maybe I shouldn't do that. They said in the circuit. So why don't I say the circuit is in the same direction as the capacitor? When it leaves the capacitor, it does that. And so there's no sign switch over. So I'll keep the negative because I'm just looking up on your author's answer. He keeps the negative. And I don't want that to confuse anyone. So, all right, I'll keep the negative. But other than that, then I can come back here and grab my calculator and kind of do the same thing here. I can go this 847 times 10 to the negative 3 for the time at 1 millisecond. Hit enter. And I guess I want the sign of that number, so I'm still in radians. And then I can multiply that by the 847, and that by the 180. And I got to be careful, micro. So this is 1.14 times 10 to the 1, 2, 3, 4, 5. But if I'm looking at my units here, this is a micro, this is a coulomb, this is the angular frequency. So this is radians per second. Now, a radian is not a real unit, it's more of a qualifier to say that, hey, remember I'm dealing with real numbers, I'm dealing with radians, I'm not dealing with degrees. So like we did a lot of times in mechanics, we'll just throw out the radians if it is just making us more confused because it's not really a real unit, it's a clarifier. And then, leaving the negative there, this right here is 10 to the minus 6. So this 10 to the 5 and 10 to the minus 6 is 10 to the minus 1. This would be 0.114. And then coulombs per second would be amps. So negative 0.114, although now I'm looking at the book, your author does it 114 milli, so it switches it back to milli amps. All right, nice. And then there was no D, so we'll call that one where it is. Okay, good. Let me move those over and get those ready if anybody asks about that one. 45, next on the list. 45. Good. And the time is 1:50. Let's see, this is our second session today. So when do we break? 2 o'clock? Yeah, 2 o'clock. All right. Let's get this one started. Might go over, but these tend to be a little shorter than some of the other weeks when I had 10 minutes left. I knew the problem was going to take 40 minutes, but hey, we needed to do them. So we just went a half hour over. But this one, I don't know how long it is, but I don't think it'll be much more than 10 minutes. I think very likely at least 10 minutes. But let's read it together here. 45 says, consider the LC circuit shown. Okay, so more of this LC circuit. So maybe we'll go faster. We've been talking a lot about the LC circuit, where we have L equal to 500 millihenries and C equal to 0.1 microfarads. A, what is the resonance frequency? And again, notice they say omega. So they're talking again about the angular frequency. And so remember I told you earlier that went back when we did, I guess it was 40 here, or was it earlier? No, I think it was 40, where I kind of said, you got to be careful in this discussion because there's a frequency, a regular frequency, and an angular frequency. And we want the angular frequencies when we're doing the math. But when we're just talking about it with somebody, we like the regular frequency. So I call the regular frequency, which really is just frequency. I shouldn't use the word regular, but I just like to make it clear. That's more of a physical description. Whereas when we start getting into the math, we want the angular frequency. So the author would be better off to say, which do we want? And sadly, we're often careless on what are we talking about, the regular frequency or the angular frequency. So here, I think he's a little careless when he says the resonant frequency should be the resonant angular frequency will make it. But nonetheless, it is the same formula that we looked up and pointed out before in number 40. So I'll just put it here. The resonant frequency would then be 1 over the square root of LC. So using my calculator here, or did I put that calculator? Here it is. Let me put in my numbers. So my L is 500 milli. 500 milli. Okay. And my C is 0.1 micro. 0.1 micro. And so if I multiply those two together, I get LC. Now let me take the square root of the LC and let me take the reciprocal of that. Okay, so I've got 4,472, and it would be radians per second. Okay, so that's pretty straightforward, just a regular plug and chug. But I think this one might go a step further. If a resistor, yeah. So all of this was the frequency without a resistor in it. It's a little more complicated with the resistor, and it does have an effect on that resonant frequency. So if a resistor of 1 kiloohm is introduced into this circuit, what is the frequency of the damped oscillation? Okay, so maybe a quick summary here. The problems we've been doing recently have been what we call LC circuits. And if you plot either the current, the voltage, the charge, I'll just do charge since that's what I talked about before, versus time, you get this sinusoidal pattern. And it keeps doing this in theory forever because there's no loss of energy. There is no resistance. Now, of course, a real circuit, you can't get away from resistance. You may not put a resistor in there, but just the wires themselves, and especially the small wires that wrap around, they're kind of long by the time they make up that inductor. There usually gets a significant amount of resistance in here. So what we like to say is a realistic CLR is an LCR circuit. And that one, as you might guess, if you started with a charged capacitor, would oscillate, but every cycle would lose a little bit of energy because as it goes through the resistor, we are losing energy, or you might say converting energy into heat. So we no longer have it part of our electrical energy. And it tapers off. And of course, to understand more of a realistic circuit is why we spend some time talking about the ideal case of no resistance. So up until this point, we've been doing problems with, no resistance. But if you throw one in here with resistance, it dampens. And so we say the frequency is going to be an omega sub D, a dampening frequency. And it kind of looks like this one. Like maybe before I come back to the one without resistance, let me write it as the square root over the whole thing. We don't usually write it that way because the top would be just the square root of 1, and we just want the square root of the bottom. But if I write it this way as a square root over the whole thing, you can see how the resistance has modified the frequency, because the first term is a 1 over LC. And then the resistor has an effect. I think there's an R and an L and a 2 and a square here. But at the risk of remembering it wrong, and definitely not deriving it, your author even says that, hey, back here in section 5, let's go ahead and derive it when there's no resistance. It's not too bad. That you can handle. But then in section 6, the author goes, all right, let's do it again with our circuit. And so here's kind of that single pole double throw switch. So he's got it set to A, and that charges up the capacitor. Then it moves it from A to B, and the capacitor discharges through the inductor and the resistor. Although, like I said, in reality, this R is really probably in the wires that make up that. So kind of just separating them for our own physics and engineering knowledge, but it actually is oscillating in here and losing energy each time. And on the next page over, actually, here's a nice picture of an oscilloscope. In the video lecture, if you got a chance to see it, I hope you have, you'll see me do it. I kind of capture it on our scope during the video lecture. Here's kind of a graph of the charge oscillating and then tapering off. Here's kind of the author over here going through the work on it. But what I want to grab your attention to then is his results, which is to say, this is the equation of the charge, and it has these two important factors. It has the oscillation, so there's the cosine of the dampening frequency, and there's an exponential decay. And this dampening frequency is listed down here. So there, oh good, I did remember it right. So there's the R, the L, and the 2, and the square. So again, without me deriving it, and I don't think I did in class, like I said, it really involves math 220. And so that's a little beyond the scope. And so your author says, let me just give you the answer and you put it back in the equation, because you can do that. You can also understand how the equation from Kirchhoff's laws come, but actually solving it is a requirement of physics, of math 220. So probably half of you could solve it, because half of you are in 220 now or already took in 220. And maybe even more than half, but that would be my rough guess. Anyway, so what I want to do in this problem is just to say, this is what the author is giving us here. So we can put this number in. And so 1 over, and I'll put the numbers in again, but we already know that this would have come out, just this square root of 1 over LC. That's what we did in A. So we know this is going to come out to be 4,472. So you can see that the dampening frequency is reduced by something. And it's reduced in relationship to the resistance. And it kind of makes sense. If you have something oscillating and then you kind of restrict it from oscillating, its period spreads out. Its oscillational frequency goes down. And so that's exactly what I get when I read the math. I see that I get the original without any resistance and then minus something. And minus something really depends on how much resistance. And really, it's how much resistance I have compared to the inductor. So the inductor is helping the oscillation. And so it's like, okay, how much resistance do I have? Not just absolute value, but how much do I have in comparison to the inductor? The 2 is a little surprising, and the square might also be a little surprising unless we study this a little deeper. But let me put in those numbers here. All right. So what were these numbers again here in 45? So the inductance here is 500 times 10 to the minus 3. The capacitance is 0.1 times 10 to the minus 6. Now we're going to put in a resistance of 1,000 and divide it by a 2 and divide it by the 500 times 10 to the minus 3 and square that. All right, so let me put all that into my calculator. And if you let me save a little bit, 500 times 10 to the minus 3 is just 0.5. And 0.1 times 10 to the minus 6 is just 10 to the minus 7. And so let me do the same thing here. This is a 0.5. In fact, 2 times 0.5 is a 1. Okay, so with that in mind, and maybe saving a few keystrokes here, I will go for this first term, 1 divided by, and it looks like a 0.5, also divided by a 1 times 10 to the negative 7. Okay, so there's that one. I'm then going to subtract. It looks like I have 1,000 squared. Well, that's 1,000,000. So 1, 1, 2, 3, 1, 2, 3. And now I will take the square root. So this is 4,359 radians per second for the new and what we call the damped resonant frequency. And again, notice it has gone down a little bit. We had 4,427. You throw in a resistor and opposes it a little bit. Has a little change. All right, and I believe there was a part C here. So I'm going to go to page 2, part C, even though we're a little over our break time, but it's definitely worth completing this. What did C say here? What is the percent difference between these two? So they want you to see that it's lower, that it drops down. Not too much. In fact, a lot of times when you're just roughly doing these things, you can do something like this, that you literally hooked up a capacitor and inductor and go, well, you know what? There is some resistance because of the twisting, but you can just kind of skip over this dampening frequency and then just do the LC without any dampening. And you know that it's going to be a hair less than that. But if the resistance isn't much, it's only a hair less. And so you can see we're down a little bit. In fact, that's how I'll do a percentage. So let's look at the change in the frequency compared to the original frequency. And then, of course, that's a fraction. So we'll multiply it by 100. So that's how you do a percentage, right? Part over the whole times 100%. So the original is the 4472. And the difference, I guess, would be the 4472 minus the 4359. So it has gone down by 113 radians per second out of 4472. So out of 4472. So that's the fraction, and then multiply by 100 to make it a percentage. I would say it has now decreased by, well, that's more than I thought it might. But I guess it is 1,000 ohms. That's quite a bit of resistance. But it dropped down and did make a change of 2.5%. So 2.5% is not a big number, but it could be a significant number. It depends on what's going on. All right, well, let me swing over here and check the answer. 447, 436, 2.53. Nice. Percent lower. All right. Well, good. All that worked out well. All right. All right. And I think we'll take our break. You say you sent me a. Oh yeah, I know what you were saying. You sent me the little graphic one that I could do. Yeah. Thank you. You did send me that email, and I like that one. Although the only reason I didn't use it is just because it's so handy to kind of drop this in the screen. But I don't know. Maybe if it's hard to see, I could switch. But see, sharing my screen. Oh, you know what though? You just reminded me. Also have app of the TI calculator. So I could do this. Oh, but this isn't probably a good idea because, oh yeah, it's blocked. I can't even clear the screen. What I use to hold my phone blocks part of the screen. It makes it challenging to. So maybe I'll just stick to the old school calculator. Thank you. Cool. So, and what's the app's name? Good question here. I got it a long time ago. Actually, interesting enough, let's see, here it is. What's that? In the part of my calculator is kind of blocking. Is that a G? I can read it on my screen better. GRAF. It looks like that's an N. CAIC. And this is for the 83. And I got this back when I did the 83, and kind of a funny story. This is the first, and actually only, no. I did get a second one. I used to say only, but it was the first app I ever paid money for. I was like, I'm not paying money for these apps. And so I got all these different apps but you know, like right next to it is Gas Buddy. Hey, I'd love to find a good price on gas, but when the app's free, I guess the Smithsonian Channel was technically free. The app was free, but you know, I have to pay for the subscription to watch the show, the channel. So I got to stream it. But actually, this one down here, the Adventures map, that's cool. That is a really cool. I paid for that one, and that one you can download. I love it when I'm out hiking, especially last summer. I was in the redwoods, and I could download maps of the redwoods, and it superimposes it. But here's the best part. It pinpoints your location with the GPS. So if you're way out in the woods and you don't have a phone signal, or you can't use a regular map, you know, like a Google map, you got the map downloaded in the app, and then the app uses your GPS and superimposes it. Well, I guess technically you don't pay for the app, but you pay for the map. And so if you decide you're going to this particular part of the country, in my case, it was Northern California, I had to buy a map for that. And I actually had to buy two so I could cover the two places I was going. But anyway, it was so helpful. There was a couple times I was deep in the redwoods somewhere and the trail split, and I was like, oh, I wasn't real sure. And I pulled that out, and I think I paid like 50 cents for it. I'm like, okay, this was a good 50 cents. All right. Yeah. Yeah. Well, I don't mean to. Hopefully, I didn't bore you too bad. Well, I'll call it quits now from our break. We'll come back, and then you said you sent me some pictures from chapters. Oh, for the homework. Yeah. All right. Awesome. And I will be back. And there's still another one on your list, 63. So we'll come and do that one after the break. All right. See you soon.